In this video, we show that the L2 space, the space of square integrable functions, is a metric space. Before going to provide the proof of this, we denote some basic properties of metric spaces. dxy is the distance, is this length here, and this can be written as minus y minus x. So this is dyx. dxy equals dyx, which is the symmetry property. Another property is that if x and y are equal, d of xx equals x minus x equal to 0 equals y minus y dyy. This is the second property. So we are dealing here with metric space. We're dealing with lengths, and usually these are in functional analysis when we want to find lengths of vectors and work in lengths in vector spaces using lengths between vectors. This is the second property. Then we have that so this is the symmetry property. This is that if x and y are identical, then this length is equal to 0. The other property is the following. So it's x minus y. We can add and subtract an element z. X minus z plus z minus w. Now we use the triangle inequality. And this is x minus z, the norm of this, plus norm of z minus w. This is dxz plus dzw. That's the third property. And now let's assume that we have d lx ly, where L is a scalar. Then we have lambda x minus lambda y. We take common factor lambda x minus y. So this can be split to the norm of lambda times the norm of x minus y. So we end up that we have lambda times the norm of x minus y, lambda dxy. And this is the fourth property. We have dxy equals dyx, dxy equal to 0 when x is identical with y. Then dxy is bounded by dxz plus dzy, and the fourth property, d lambda x lambda y equals lambda times d of xy. We spit out the lambda, the constant lambda. Now we use these properties in order to show that the L2 space is a metric space. So now let's take the norm of let's take this norm. F minus g squared d omega So this is the norm, the L2 norm of F minus G in omega. Now let's take dgf. dgf equals the integral over omega g minus f squared d omega I can write it in the following way: minus f minus g squared d omega and this is the norm of f minus g in L2. So is the d of fg. dgf equals dfg. So the symmetry property is satisfied. Now let's pick f to be identical to g. We have d of fg equals d ff equals d g. So this becomes equal to 0. This becomes equal to 0. The second property is satisfied. Now let's take dfg integral over omega f minus g squared d omega raised to the square root. The square root of this. So here we can write this inside f minus h plus h minus g. You can write it like this. So this is the L2 norm. The L2 norm, and we can use the triangle in Minkowski's inequality. And this is dfh plus dhg. And the last case, so this is satisfied. And the last case, d lambda f lambda g, where lambda is a scalar. So you can write this as square root of this integral over omega f minus g squared d omega, and this you take the square root. So what you get is lambda times the integral over omega f minus g squared d omega and the square root of this. And this is the f minus g norm in L2. So since all the properties are satisfied, L2 space is a metric space.